Hello and welcome to Metaphysics. This is the third episode, and this is actually part one of a three-part series. And in this series, I'll be talking about vectors in Fourier series. So it's a series about series. And we'll be using our understanding of vectors to help us learn something about Fourier series, or at least think about them in maybe a different way. So we have probably some vague notion of what a vector is. I'm assuming many people in my audience have taken physics or math classes before. So usually our vectors, kind of in the most abstract or maybe intuitive sense, are just some arrow that points in some direction with some magnitude. So we usually maybe give them in coordinates r, theta. It's usually useful to kind of take this intuitive picture of a vector and actually put it on a basis so we can do calculations. So in this case, I'll choose the usual xy basis in the 2D plane. So now our vector lives somewhere. Give it a name, r hat. So this vector now lives on this coordinate plane. So x and y is the basis I've chosen. I could have picked something else at an angle, but I've chosen x and y. The next thing we can do is we can try to describe this vector r in terms of my basis vectors in the x and y direction. So I know that this vector has a component along the x direction and a component along the y direction. And if they happen to be A in the x direction and B in the y direction, I know I can represent my vector as r is going to be equal to A in the x hat direction plus B in the y hat direction. I think this is fairly basic if you've used vectors before, but we'll be using this intuition that we already have to learn something about Fourier series, which maybe we don't find as intuitive. So again, things to take away from this, we had to choose a basis because we wanted to know the components of our vector in that basis. So how do we find the components? Well, in general, we know that we can project vectors onto axes. So geometrically, we can kind of think about this as taking our vector and to project it onto the x-axis, we squash it down and we get the projection in this direction. And to get the component in the y direction, we smash our vector in the other direction, and this is y. This is nice. It's a good geometrical picture of what we're doing to find the components, but in general, we're going to want an algebraic picture. So I'm going to create some notation. So if this is my vector, I want to know what the projection onto the x-axis of this vector r is. So in this case, I know it should be A, because that is the component here. So, but that's not very useful. If I have some other vector, it may not be A. So I want to know what is actually some function that I can use to project this. So if you've worked with vectors before, you probably know that the way to project r, or to get the component of r in the x direction, is to dot it with x hat. So this will give me this term here, A. Likewise, if I want to project into the y direction, so these are subscript x and y, my vector r, this should give me B. And the way to do that is to take r and dot it, this time with y. So this isn't the one way of thinking about this is I didn't have to choose this function. I could have just said like, oh, I just grabbed the thing here. But this is a nice mathematical representation for what this projection is doing. And it kind of has all the properties that I want. Like this will always give me this term. It'll never give me this term. So it kind of satisfies a lot of nice properties that I want for something that I think about as a projection operator. So after I learn how to project things, I want to rebuild my vector in my new basis. So far, I have my vector. I know I want to project it or I want to think about it in this xy basis. So kind of the most basic first step we know is that I can write my vector in terms of its components. Well, how do I get these components in general? So the way on the last slide we found out to do that was to get A, we projected on the x direction our vector r. So that'll give us A, and then I need x hat to tell me that A goes in the x hat direction, or I'm going A in the x hat direction. And I do the same thing in y. So it'll give me B, and then I need to multiply that by y hat. This is maybe doesn't seem simpler, it doesn't seem more useful, but we'll see when we start doing Fourier series that this is a nice way of thinking about building up this vector r. So finally, I can write it in the kind of most abstract way. So I'm going to let this variable e run over my basis, so x and y, and I need to sum the projection. So both of these are projection in some direction, so in the e direction of my vector times the unit vector of that basis element. So to write r, I sum up over all my basis elements, I project them onto that element, or onto the unit vector, and then I multiply it by that unit vector. So this is how I kind of rebuild my vector r in this xy basis. So just to recap, there are a couple of important things that we want to remember about kind of our knowledge of vectors when we start talking about Fourier series. So we want to choose a basis. So xy is our basis. Obviously, we want our basis to be kind of complete. It has to span the whole space. We want our basis to be orthonormal. So all of the usual things that we mean when we choose a basis. We have to figure out what our projection operators look like. And these can be really anything, but they need to satisfy certain properties. For instance, we want the x projector to kind of grab the x component and not grab any of the other components. And then we'll want to think about rebuilding our vector using these projection operators and the basis unit vectors. And so next time, we will use all of these ideas to talk about how to create and understand Fourier series. All right, I'll see you soon.